All right, looks like we're good to go here. So today is February 12th, and let's do announcements. So tonight we're going to have the ACM presentation on big data. So we'll end at 6:15, and I'm going to set the clock accordingly. Okay, that's good. And I also sent an announcement. I posted an announcement on the Facebook group. So we're going to have a faculty candidate coming in to interview for a full-time position. Her name's Dr. Sarah Sood, and she's from Pomona College. So she looks at machine learning in conjunction with social networking. So it's quite interdisciplinary, quite interesting. So she's going to talk about her recent work on detecting insults on social media. So, there's a natural language processing element, perhaps, and, machine learning, data analytics, etc. So it's going to be at 10:15, from 10:15 to 11:15. We're going to start in the 4th floor conference room. So Lewis Towers 415, and if there are too many people, we'll move to 410. So if you can make it, you're more than welcome to join. I will also try to set this up so you can join through Adobe Connect at the URL I provided in my Facebook post. So you can come in as a guest, and I will just basically approve whoever wants to join as a guest. When you're prompted to enter that room, you will see. Okay. One other not so a little less pleasant announcement for me to make is that I've made progress on a lot of stuff, but I still owe you the graded project 1. So I was focusing mostly on preparing stuff for today and for going forward, including a project 2B, to make sure that I would keep you engaged. That's why I gave slightly lower priority to project 1, and you probably know more or less how well you did. So, but I will get to this over the next few days, for sure. So thanks for your continued patience with that. Okay, so project 2B. If you look at project 2B without the right guidance or adult supervision or whatever you want to call it, your head might start spinning. But here's how we'll do this, okay? And we'll take a look at the end. I mean, don't look at it yet. This is very deep and challenging material in some ways, but it could be quite rewarding to get to a point where we develop a certain mastery of this material. So it goes a little bit in the direction of what I try to motivate here through this monoid example. So the idea is basically, the overarching theme is to be able to express certain abstract structures, very general structures, in such a way that we can do certain things on these structures. So we can express behaviors once, for a certain set of behaviors once, and then all instances of these abstractions will have those behaviors available. Okay, so I'll give you an example for monoid. Duplication, x plus x, right? So if x is an int, you get 2 times x. What if x is a list? And well, I have to tell you, the operation is list concatenation. What would you expect? Pardon? Well, you have to have something that's like 2 times x.
It's actually, when you concatenate it, it makes sense to call it 2 times x, right?
So what would it be for the list? of what? So you have the list X, right?
Yeah, the two lists.
The list with it, right? The list with itself, right?
Yeah.
I mean, so that's what I had in mind. So basically, if you concatenate any arbitrary list with itself, it's like the list two times. So with monoid, if you say, well, I can do the duplication, I can express that just for any monoid. So I can say, well, as long as X is a monoid, the duplication or the duplicate of X is X plus X, where plus is whatever it is for that particular monoid. So addition for integer or list concatenation for list, then it works. And it'll work. So you have to think about the software engineering implications here. So you can write one function, and it'll work on a very broad class of instances uniformly. So this is actually very powerful. And that's the kind of stuff that we'll explore. So we'll get to that at the right point. So that's kind of the direction in which we're heading here with Project 2B. And trust me on this part, we'll manage, let's say, the deadline accordingly to the progress we're able to make. I cannot predict, so I tentatively set the deadline for the 24th, which is probably ambitious. So depending on how much actual progress we make, we'll manage that deadline. We're going to keep this as a rewarding, low stress experience. I mean, we want high challenge but low stress, right? That's what I'm shooting for here. So we want to get into this stuff and learn kind of the deeper foundations behind these structures, but it will take some time. But then also, we're not going to look at it with formal mathematical rigor as much as more in the way of trying to develop a working intuition. So being reasonably comfortable with what these things can mean for us in practice. Kind of at the level of the example I gave here, right, that I think you can relate to. So it's better, right, being able to write a duplication function once and have it work for these existing examples and other future monoid instances I come up with, right? So from a software engineering point of view, I write it once, and it covers a vast number of actual situations. So that's highly beneficial. So the other announcement is, as part of these, this is really not such a big announcement, but as part of these explorations, a little project was born here. So it's called Scala K, and these are small extensions to the Scala Z library that will start exploring. So Scala Z is quite vast and powerful, but ultimately it's actually quite nice and simple in many ways, once you kind of get the hang of it. But there are some things that I added to that, and I just got done before class pretty much with the last simplification step. So it'll allow us to learn some of these things more easily. It'll make things more approachable. So the quick start will not make sense yet, but it'll make sense. And there's a Greek letter, so that's on purpose. It's kind of a little bit of a joke, I didn't have to do a Greek letter, but the thing is, nowadays you can just use Unicode characters in your identifiers. So this is in the literature a common symbol for this particular purpose. Anyway, this will make sense soon, probably by next week or so. It'll all make pretty good sense. We'll see. All right. Anyway, so this is the one that was called Algebraic Explorations-Scala, so I just renamed it to Scala K earlier this afternoon. All right. So you're kind of part of this project from the very beginning, and it's exciting to me at least, and we'll see if it's contagious enough. We'll see that soon. Anyway, the thing we need to look at to continue from last time, where we needed to wrap up a few things. So through Project 2A, you have now a decent amount of hands-on experience with non-generic algebraic data types. So you have these shape trees. You realize that these are recursive types. So shape is recursive because there are certain variants or node types that have shapes as their own children. So when a node has the kind of thing that it is part of also as its children, then you have what in the patterns community is called which pattern? So the group node in shape, which pattern does that reflect? Composite, exactly. That's right. So composite often includes some examples of decorator, and we have location as a decorator, and so on. So that's kind of the connection between algebraic data types and the composite pattern with decorator. And then you saw how the behaviors corresponded to the visitor pattern. And there was this nice discussion that I think you started on Facebook, right? And you contributed to that as well. So that trade-off that you probably observed in your OO class, where it says, well, if I introduce the visitor pattern, I basically lock down the tree structure. I will have a hard time introducing different kinds of tree nodes after I define the visitors. That is widely recognized. That is part of the trade-off. So if you do it without the visitor and you just define the behaviors as methods of the nodes, or the data structure itself, then you retain the extensibility of the data structure at the expense of, as Michael was pointing out, of kind of putting structural concerns and behavioral concerns together in a single group of objects, right? That is one concern. The other concern that is kind of a consequence of this is that if you want to introduce a new behavior, you have to add it to each class that's part of this data structure hierarchy. Okay? So that is what you get. That is the situation you face when you have just an ordinary non-visitor object-oriented data structure as a hierarchy using composite with decorator without visitor, right? So it's easy to add different kinds of tree nodes or data structure nodes, so the structure is extensible, but it's a little painful to add new behaviors. Okay. On the other hand, if you say, well, let's make it easy from the get-go to add behaviors, because I cannot anticipate what behaviors I will need down the road. Okay, so let's equip this data structure immediately just with a visitor, with that kind of hook to throw a visitor at an instance of the data structure, but not put any other behavior in it. So the data structure is just structural, just navigation, how the different nodes relate to each other. And the only behavior is just the ability to receive the visitor so that the visitor can do its job when it looks at a node in that kind of structure. And then the behaviors can be very easily extended. You just write more visitors. You don't need to touch the original data structure classes. So this trade-off is known as the expression problem. So I posted a link as part of the Facebook discussion. That's a widely known, widely researched, and well-described trade-off, and it's interesting. And in the Scala with Style keynote by Martin Odersky, he actually kind of ties these things together quite nicely. So he's explaining how making the data structures extensible So avoiding visitor, makes sense when you have an open system. So for example, a simulation where you might have a common interface that all the different things that are part of your simulation might have. For example, make one move. Let's say you have rabbits, you have wolves, you have plants, like this kind of ecosystem simulation. And with every time slice, each of those things that are in there, these living things, animals and plants, they make their move, which could be for a plant, it could grow a little bit, or it could produce fruit, and for the animals, it could be actually moving physically, from one location to another, etc. But they would have one interface in common, and that's why it would make sense to inherit from a common interface that specifies what behaviors those things have. So it would be a relatively small but fixed set of behaviors, so a fixed interface. On the other, so that's an open system assumption that you might, you're designing this to be extended later because now someone wants to say, okay, for solving real research problems, let's say you have an ecosystem without humans, and then you want to extend it, you want to say, okay, let's add some humans and see whether it goes better or worse for this ecosystem by adding those, the simulation of the presence of the humans. So does that make sense? So that's a type of system you want to keep extensible in terms of the kinds of objects you have in there. Whereas when you have something like a set of classes representing arithmetic expressions, that you could take the point of view that that's a closed set of classes. But I might want to do different kinds of more or less interesting things to them, such as counting how many shapes or expression nodes there are. Maybe if it's an expression, I want to evaluate it, or I want to transform it by optimizing it or whatever. So there you want the behaviors to be extensive, but that usually happens when it's a closed system or like a fixed language, like arithmetic expressions or shapes. Okay. The shapes one, though, you might need to make this kind of trade-off. You might say, ooh, I do want to extend the kinds of shapes. So that one I think is probably more on the fence, where I could say, ooh, which should I, for the shapes, should I make an open world or a closed world assumption? And you could say, well, there are arguments in favor of an open world, such as adding new interesting kinds of shapes like polygons or triangles or, well, special case of polygon, but polygon would be a good addition, where you might not be able to predict in advance what kinds of things you want to have in your environment. Does that make sense? So that's the overall kind of background for this trade-off. But we're looking here because I'm trying to give you a contrast to the familiar object-oriented way of thinking that most of you are likely to come in with. So we're looking at it more from the from a side where we're separating structure from behavior, and we're exploring the consequences of that. And I think there's an earlier. I think it's probably here. Oh no, I propagated those things properly. Yeah, so this separation of concerns here, right? So one thing is just the pure structure. Let's say, how are the different things in your data structure connected? The other one is what kinds of things can you put in the different nodes? What do I have living at this kind of node or there? Then traversal and processing. So traversal, like navigation, moving from one node to another, and processing is doing actual stuff with what I'm finding there. So in which of these categories would you put something like the fold method? I actually like that answer. Why not processing?
Processing as well.
Well, so that's the question, you know.
I think it's both.
There you go. Someone's Exactly. That is the separation of concern. So the fold gives you this separation, you know, it kind of articulates this for you. It sets a boundary. The fold takes care of the traversal transparently. And you plug in something that you want for the processing. That's the beauty of it, exactly. So we'll explore this line of thinking a little more, you know, and then we'll generalize it to, you know, we're looking at these custom domain models such as expressions, shapes, org charts, whatever. These are simple examples of custom business domain models. They all have kind of a tree-like quality to them. But you know, we're also looking at linear things like lists and maps. So anyway, excellent. Okay. So back here, so basically, I've organized everything in the Misc exploration Scala project, and then the other stuff is now part of the Scala K examples subdirectory. So that's going to be our next step after wrapping up here. You know, so let me see again here. Yep. So just to wrap up briefly, the this algebraic data type stuff from the, let's say, conventional, straightforward approach that, you know, that's built into the language in the form, in the case of Scala, in the form of this sealed trait and case class idiom. Okay, so basically this org chart example, you know, that's at the level of your kind of your shapes example. Maybe this is even a little simpler. So I think we looked at this. I incorporated some of these comments, and then you can write the size method and the depth method, and they basically look the same. And I think, yeah, we did do this, right? So here I had to put 1 plus, and then doing, instead of sum, doing the max of the depth of the subtree. That we did go through, right? So we're already a step ahead here. So here's another Unicode character, because I didn't want to keep advertising Yahoo, you know, as saying, okay, it went to the end, you know. So I'm just printing a black square now. Okay.
Do you use the Unicode numbers to?
No. Here's what I did. So I googled Unicode black square. It popped up, and there's a whole page about the numbers and different notation. But then there's actually also the character itself. So you just paste it. That's all it took, you know. But the certain characters you can make very easily with your keyboard, you know, like mu. If you do Option M, you get a mu. So that's easy. But you know, these others, I just paste them. That's right. You could probably look at that exactly, and you can do the Alt and then the keypad. Okay, so the other thing I wanted to look at briefly with respect to the org chart is, well, the role of genericity, and that's basically backing up here for a second. This separation, so structure and content. So if I say, well, whatever I store in each node of my data structure is generic, I get a lot of flexibility in terms of content, in terms of whatever I want to put in there. And you will see in conjunction with the org chart that can be useful. Now, this actually takes care of this other thing I mentioned also as an experiment. You know, if I define map and flat map for my org chart, I can do a for comprehension over the org chart. You know, what I was promising earlier. You know, so now all of a sudden the org chart can be plugged in here, and you know, the stuff just works, because really these things, all the ones in the middle get translated to flat map. The one at the end gets translated to map. Okay. And there could be conditionals in there, and those get translated to filter. And that's really the connection. So the four comprehensions are tied directly to these higher order functions. Anyway, so that's really an aside. What I wanted to emphasize is the following. So if we make the org chart generic in our content type A, so if we say, okay, if we have a P node for person, it can store a data value of type A. So we'll make the org chart as generic as list or sequence, where we can store arbitrary item types. So we decide, well, in this org chart we have one item type, in this instance. In this other org chart instance we have some other item type. So we're about to see that that is useful. Okay. So everything that was before, the A was string, we generalized that to A. And before it was just node star, meaning 0 or more nodes as children. And now that is a node of A. We just have to kind of pass through that generic item type. And you might wonder, what's that plus there? Well, okay. So the plus means, and I'm just going to say this briefly, because otherwise, it opens a can of worms, we get distracted and so on. We really want to look at mostly what these things can do for us, in solving actual problems, but at the same time understanding the relevant deep structures here. So the plus A means that the data type is covariant in A, and covariant means if I have, let's say, a tree of, let's see, if I have a tree of person, or an org chart of person, and if, let's see, where's that thing here? So let's say if we have person and we have a subtype, let's say employee, then an org chart of employee is a subtype of an org chart of person. This is covariant, meaning, once you apply this structure to it, it's in parallel with the original is-a relationship. Okay. That's covariance. Contravariance would be if when you put it in the structure, it's the opposite. Okay. And normally when the structures are immutable, you get this nice covariance. When things become immutable, it gets a lot more complicated. Then you might get contravariance or invariance in some cases, so it can get messy. But anyway, so the plus allows for the covariance to happen. Okay, so now let's rig up a little instance of the org chart. You notice how, other than the map and the flat map, which are these kinds of generic things that allow us to plug these things into the for comprehension, they don't have any behavior, so it's just structure and this kind of generic behavior, support for the for comprehension. So here's the outfit, or whatever, some organization, which has, a little organizational hierarchy. And you could see that here, instead of just plugging in strings for each node, I'm plugging in a name, which could be a name of a unit or person, and a budget of the unit or salary of the person. So here I'm benefiting from the fact that I opened it up for more than just string for each node. Does that make sense? And now I can say, for example, I can map, because I defined map. I can apply map, just like I can apply map to a seq or a list, where the argument that I pass to map is applied to each item, each data value at the node, and I get something that has the exact same structure. It's isomorphic structurally, but the item values are the results of applying the same function to the original item values. Does that make sense? So the notion that we saw for list or sequence, those kinds of things, where it's very easy to understand map, it applies equally well to nonlinear structures. So you basically copy the nonlinear structure, just the skeleton, and then each item in the original, you apply the same function, and you put the result values in the same corresponding places in the resulting tree structure. Okay? So here, if we say, well, for each item, we'll apply, so we'll map onto the tree this function. What does this do? This looks kind of weird. And you might not yet be familiar with the tuple selector, but you will be right now. So the first underscore, so it's a little bit of throwing you into the cold water. So the first underscore, you're already familiar with this. This will be just the anonymous argument that will be associated with each item that we're mapping over. Right? So that's that. So this, it'll be applied basically where in such a way that the underscore will be each of these string number pairs. Okay. All right. So now the underscore, the anonymous argument, will be a string number pair, and a pair is a special case of a tuple, which is just a product type or a combination of multiple pieces, like a class with public member variables, but we don't have to introduce a class name for it, nor do we have to introduce names for the member variables. In the tuple, it's just whatever order they show up in. So here it's string paired with int. So the first thing of that, underscore 1, that's a string, and underscore 2 would be an int. So that's the tuple selector. If you try to select something that isn't there, you get an error. And oddly, these things start at 1, whereas in most other cases things start at 0. But who knows? I mean, that's just the way this is designed. So 1 is the first thing in the tuple, and so on. And these are finite in length, but the different component types that are part of the product don't have to be the same. That's why here we can have a string tupled or paired with an int. So the string has a length, so we can apply the length method. And that's why here, and then what is that? The data. Okay. Good question. I have to remember.
Does that assertion pass?
Oh yeah, sure. Well, we'll try it out. Yeah. See, so data is just whatever I have in each node. So here's what happens. So let's envision what we get up to here. What is the result of applying map to a tree? What is the result? What does the result of applying map to any structure look like? No, it really no. So again, let's distinguish between the map method and the map data structure, which is basically a set of key value pairs, right? So this is the application of a map method, which means we take this function and we take the original structure and we get a new structure that's isomorphic to the original structure, but the items are transformed by applying this function to each original item. That's how we get the new item. So up to here, what does the result of applying this map method to org look like structurally? Sure.
Like the same structure, but with length instead of OU object, or each of the nodes.
Okay, so it's very close. Okay, so to be really clear, right? Yep.
What the whole thing does is like it counts the number of characters in the string in the data of the first element.
That's right. So what does how would you describe the result?
The length method has to be applied on the data of the first.
Right.
Item, right?
That's right.
So we apply the length method to the next.
Right. So let's try to take advantage of the separation of concerns between the actual structure and what value is stored in each node of the structure. And the map operates on the latter. It preserves the former. Okay, so you're expressing that. So, but just to be really clear, I mean, what gives this org chart the structure are the OU and P nodes. So the map will not make those disappear, nor should it. Does that make sense? So in other words, you get basically a copy of this same structure, but instead of having this string int pair, you have just ints, which are the lengths of the original strings. So you would have, for the top level node, you would have the 10. So data, that's just org. The tree, you access the tree through its top level node. So org is this OU node, which happens to have children, but it also has that data value. And once you map the length method over these things, the top level root node will have a data number, a value of int 10. And that one will have, the person node here will have a data value of int 3, and so on. So that's how this function gets applied to this node, to that one, to all the data values of all the nodes. Yes?
Would it replace the string with the new value, or would it append it to the tuple, where would it store it? Does any of that data get lost, and where does it store the 10?
Okay, excellent question. Right. So these are immutable structures. So it'll create a new tree with the same skeletal structure, but with the results of applying this map, the argument of the map method to each value. So in other words, the original tree is still there. It's immutable. It doesn't change. And there's a new one where all of the old data values are replaced by the result of the method or function we're passing to map. So in other words, there are only ints in the new one. Only the lengths of the strings in the old one. Okay? And that's why this assertion passes. Or I could say, I could probably add another assertion. If I wanted to say that the first child of the root node has data value 3, right? 3 for CEO, right? So that should pass as well. So we should be able to say children. Yep, see, it finds that. And now here we got to start from 0 because it's a sequence-like thing. And here we should, let's see. Well, no, I think we expect there to be just numbers, right? Let's see. So what is? Let's find out what the type of this is. It should be. Oh, okay. I know what the problem is. So the type of this is what? We just have to look at the definition of children. It doesn't know that it's a P node. See, it's this problem when you have a more general supertype, and then you don't. It doesn't know that it's a specific subtype, So node doesn't have a method to access the data value, even though here it could because it's common to both. Yep. That's exactly what we'll have to do. That's right. So we'll have to, in Scala, that looks like this, as instance of. It looks a little nicer, it's more conversational, flows better than a cast in C or Java. So here we can say P. But this might fail, of course, with a class cast exception. That's why we could also use a case, like a pattern matching, to do the same. Then we could handle failure more nicely. But here we're assuming it'll pass, and this should give us a 3 here. Okay. So now, as you remember, we can just run the worksheet. So also if you have a slower machine, it might be faster to run the worksheet in a terminal. Okay, so that's just a warning. See, so there is a little syntactic error, okay, because P is a type constructor, because even the P itself is generic. So we'll have to say P of int, right? So we have to tell it, we expect there to be an int inside the P. And now, let's see if that passes. And that was a compile time error. So let's see if this passes now. Yeah, so that makes progress. So, okay. So we're good. So we were able to navigate to, I got it. I lost scrolling, so okay, there I go here again. So we were able to navigate into the tree a little bit, by just going through there. But again, one would have to revisit this decision not to expose a data method at the level of node. That's probably something I should do. So let's do a little to do. That's probably going to be abstract. Okay. All right. Then we don't need that ugly cast because, casts are usually a sign that something's not quite right. They could be considered a smell. Okay. The for comprehension works, but now I wanted to show, let's see what else. Yeah, so for example, you can do other interesting map things. You could say, let's apply a percentage raise to everybody. So here we have a little method that takes a raise percentage and then a salary as a whole dollar amount, and then it applies the raise percentage, so 100 plus the percentage divided by 100, and basically increases the integer number by that percentage and rounds it back to an integer. So what we could do is we could say, okay, everybody gets let's say let's see, yes, so everybody gets a 2.5% raise. How is this expressed? We'll say, okay, we'll map, in this case, instead of doing the length of each first part of the pair, we'll say, okay, we'll map and we'll expect each data value for each item to have this shape, right? So here we're using pattern matching, which is a nicer way to bind to the pieces of a tuple or pair. So we get name and salary. We keep the name the same, but we replace the salary, or basically map to a new organization where the salary is increased by the desired percentage uniformly. So everybody gets the same increase, the same percentage increase. Okay? So this is more interesting than the length, because here we're really transforming it, and the new values are a transformation of the old values, where we're retaining part of the characteristics of the old ones, like in this case the name. So we're not replacing what was there with something totally different. We're rather updating it. You know, the name stays and the salary gets updated by a percentage. All right, so this assertion also passes because when you take the 140K CEO salary times, you know, giving it a 2.5% raise, that's what it goes up to when it's rounded. And then you could say, oh, I want to publish my org chart on the website, but I don't want to publish the salaries, you know, so I can sanitize this, and I can say, just keep the name. You know, so this is kind of like that one, but we're keeping the actual name as a string. Does that make sense? Okay. And you know, this will pass where we're checking that the root node is actually an instance of node string. So the map transformed the type parameter of the instance from string int pair to just a string. Any questions? So what I was trying to show here was the value of having genericity, or type parameter, for the content possibly stored in the structure as a separate concern. So consistent with the idea articulated here, you know, the separation of concerns between structure and content. So if you have the content as a generic type parameter, then you're getting a high degree of flexibility here. All right, any questions, comments? Okay. Great. So now what I want to explore with you next is, so we're going to lead up to ultimately the, you know, this interesting stuff at the type level, but we're going to look at it first at the function level, or values and functions. Okay. So some of these things, of course, you've already explored, so you're quite familiar with things like map, sum, fold, reverse, those kinds of things. But you know, let's look a little bit at how those things would get written. And this is also part of the Misc explorations example. So if we go to functions on lists, we can see that. So again, I'm providing at the top the Haskell-like notation of the conceptual understanding of the list type. So it's looking more like the org chart, right? Except that what's really the key difference between this list type and the generic org chart type? They're very similar, you know, but what is the one key difference? The nil is kind of like just a person node that doesn't have children. So, pardon?
Double colon.
The double colon, that's really just a syntactic notation. You know, so instead of saying something like OU, we say, you know, value double colon and then an existing list. So it's like saying the name for that is actually cons, because you're putting a value and an existing list, and you're getting a new list with it. So, or in other words, this double colon is similar to the plus colon that we saw for sequence. So it's actually the same, except that the double colon, the cons notation, exists only for actual lists, but sequence is an abstraction over list, and list is a concrete implementation. So that has these concrete patterns that you can match. So now let me give you a hint. So is org chart a linear or non-linear type or structure?
Non-linear.
Non-linear because you can have many children in that. What about in list?
List is linear.
Linear, exactly. So really the key difference is that in list, each node has exactly one child, except the nil, which has 0, right? So that's where you terminate. So a list, you can think of a special case of a tree where you have at most one child. And once you get to a place where there's 0 children, that's where the list ends. So if you decide, just to have a tree without branching, you can still express a list using the building blocks for a tree. But a list is an important enough case that it's a very common type. Okay. So remember, we had the little, what do you call it, on the quiz. There was basically a fold example, right? So here, it is the same, right? The plus colon. So this is the same example as from the list. I mean, from the test. But I mean, someone had yes.
I read somewhere that the double colon is meant for list at that time. Plus colon is for sequential.
Right, but list is a subtype of that, so it'll work with that as well, but not the other way around. So for sequence, you cannot use this on sequence, but you can use this on list, if you want. But this is a kind of a concrete implementation of that. It's actual concrete syntax. Okay. The question that we should be asking by now is, well, how do you write functions such as fold, those kinds of things from scratch? So we know that we can write a reverse using a fold. We saw that in the test. Okay. How can we write a reverse from scratch? And then the next question is, how can we write a fold from scratch? Because someone has to write the fold, right? So we'll get there shortly. So let's see first how we can write the reverse from scratch. It's just like you would write these, just like your size and depth, bounding box, those kinds of things, except we have one child. So we say, well, what's the reverse? And it's very declarative. What's the reverse of an empty list? Oh, it's an empty list. Yeah, sure. That's easy. What's the reverse of a list that starts with an item H for head, and the rest of the list is the tail T? Oh, that's easy. We just reverse T, and then the item that was at the head before, it moves to the back. So the colon plus is kind of the counterpart to the plus colon. So this is appending an item, a single item, at the end of a list. And then when you recurse through this, all of the items at the beginning, they move to the end, and at the end you have whatever was the first item of the original list, it's then the last item of the resulting list. Does that make sense? Yep.
So for the colon plus, can't you replace that with double colon as well?
No, because you see the double colon is asymmetric, right? Item and list.
Yeah. Okay.
Right? So this is that's why in a way the double colon is not as intuitive as that, because the mirror image, right?
Some functional languages, right? I think in ML.
No. This is just like ML.
Yeah.
It is the same. But I'm now seeing why we really should not use the double colon. So we should write it like this. It's actually better. So we'll reverse that, like this. See, because now we really have that nice mirror image here. I like these kinds of things. So kind of a duality that we have here. Whoops, this thing is sensitive. Okay. Okay. Yeah. So the way you can if if you're not fully comfortable with this, just play through the steps on paper or whatever. So let's say with this example, okay, so we want to reverse 1, 2, 3. Okay, we'll plug 1, 2, 3 in here. So see, this is another little thing here. Here we're saying reverse is, I think, this kind of stuff we can say val, right? Oh no, we can't because it's recursive. Okay, yeah, no problem. So we'll leave it as a def. Okay. So there's no explicitly named argument, but we're saying the type of reverse is take a list argument and produce a list result. So the rocket or a double arrow means you're taking something of the type to the left of the arrow and it produces something of the type that shows up to the right of the arrow. So the thing to the left, that's the argument type. But here we don't have a name for the argument. So the way we could write this is, for example, we could write x's, and so x's is a common abbreviation for lists, in functional languages. So it's the list of x's, and we could introduce that as the argument name, and we could write something like x's match like this, and then this would mean, okay, the function takes the argument x's, and then it matches this according to these branches, these possible case branches. But this appears redundant, right? So we could simply leave that one argument anonymous, and we can eliminate this again. So here, it's basically whatever we plug in as that argument of type list, it gets matched according to these branches. Does that make sense? So it's a little easier to read like this. Once you get used to it, because otherwise you have to kind of match up argument names with their uses. And here it just goes straight into the branching, and you see that what is coming in is a list. Okay, so if we go through this, so initially we plug in the list 1, 2, 3, and we get the second case. So H is 1, and the tail is 2, 3. So we get the 1 here at the end, and then we have to reverse the 2, 3. So we apply the function again recursively. Now we're plugging it in, we're getting here, and the H is 2. Okay, and tail is list of just 3. So we already have the 1 all the way to the right, and now for reversing 2, 3, we get the 2 here, and then we have to reverse the list just with the 3. And then that goes in here again, and then T is empty, and we get the 3, and then we go in here, and we're done, right? So it's 3, 2, 1 in that order. So that's very common, that type of recursion based on the case distinction, a base case and the inductive case or recursive case. Okay, but the thing is, you could instead use the fold, and here's your fold. So that's I could write the fold even better. I could say it like this: T and H. Okay. But it does it kind of in opposite order, because it's a fold left. Okay. Anyway, so all of these, map can be written in a very similar way as reverse. Map can be written as a fold. If you write a fold kind of like reverse as fold, where the output is or the result is a list. Okay, and then how do you write the fold itself? You can write the fold itself with a similar case distinction. So now I'm thinking, there's one thing I did mess up. This doesn't work as a pattern. We have to have, for this pattern to work, we have to have the double colon. Okay, so that's why that was there. But when you use it to build a value, then the operator is as good as the constructor. So basically, let's leave it in its original state. Okay. All right. So let's run this through quickly, and okay. So whenever you see that little square at the bottom, it worked. Okay. Then you know that it actually went through. So what I would recommend is, as an exercise, this is really good practice, and it also, this is the kind of stuff that might be on upcoming test or so. How do you write something like map or fold from scratch, or how do you express map as a fold? So the thing is, now you're starting to, I think, to see the value of fold as capturing the common pattern, the type of recursion that is common between, let's say, reverse, length, sum, right? We've seen sum, all of those kinds of things. And the fold allows you to achieve the separation that we recognized earlier. The fold gives you a way to leverage the fact that you discovered and are able to express that the traversal underlying things like map, reverse, sum, etc. is all the same, and the only thing that's different is what you chose as the result type and then the processing that comes with that, and the actual desired result, right? So the traversal is in many of these cases is uniform, and only the processing along with the chosen result type changes. So that's the value of stuff like fold. Now, of course, the map is also a very common case in its own right, as we've seen. So for trees, map is very intuitive, because for any kind of structure, because it's structure preserving. So that's very intuitive. But that means it takes care of the traversal for you. You just need to worry about what happens to each data value that the map finds. That's where your function f comes in, that you're applying to each data value. But the traversal is a concern that the map method takes care of for you. Okay. All right. So we saw how we can write our own functions, and again, the suggested challenge is, we saw the reverse, try some of these others. So map, sum, and so on. So try map from scratch. Try it using a fold. It's really good practice. Write some assertions. You can intersperse them there. And there's a really nice reference, which is, I need to dig up the link, but so there's a paper by Gibbons called the Origami paper, Gibbons Origami Programming. So if you Google that, but I'll add this reference. So it's right there. He's at Oxford, and it's really about these kinds of things. So he explores how to express more interesting things, such as insertion sort or other kinds of sort. All of these as building them up based on things like map and fold. Okay, so kind of discovering and expressing the common traversal patterns there. All right, so I'll put that in. All right, and of course, we are familiar with, or we're becoming increasingly familiar with those predefined higher order functions. Okay, and there I want to go through a little example. So, well, we saw the fold left, and I think by now we're reasonably familiar with that. And we've used map and sum and those kinds of things in the shapes project. So I wanted to show something a little more general now, and also take this as an opportunity to introduce another kind of data structure, which is like lists, but it can be infinite. So these are lazy lists that are basically, so this is, might initially make your head spin a little bit, but you'll become familiar with it soon. So it looks like a list, but there's, instead of the double colon, there's the pound double colon. And the way that works is, okay, you get the head value of type A, and then you get the rest of the stream. And unlike a list where it could basically write down the whole list if you wanted it to, or if you told it to, with a stream, it doesn't try to compute the rest until you tell it to. Meaning that it's kind of like a list. So when you're putting a stream, when you're creating a stream, you're specifying the first item, the head, and then you're specifying the rest of the stream. But it will just kind of keep the rest of the stream that it got from you as kind of the instructions of how to compute the rest of the stream when you tell it to later. So you might wonder, how could infinite structures possibly work? We don't even have infinite memory. How can that work? Well, that's a really good question, of course, and the answer is, well, as long as you never try to look at the whole infinite thing at the same time, you're okay. So you could say, I want to look only at the first 20 items of this infinite structure, or the next 20 items. So it can work as long as you always work on a finite subsequence of that stream, or a finite substructure, more generally speaking, of some infinite structure. Because, if you have tree structures where the children are stream-based instead of list-based, then that tree could be infinite also. So it's not limited to linear structures. Anyway, so it's again the kind of thing where there's a lot of theory behind it, but as long as we develop a working intuition where we can get results, we can solve problems using these things, that's a good step. All right? So let's try to compute the list of primes. Okay. And we'll just start with some explorations. And let's say our range is, let's say 2 to 20. We'll look at primes up to 20. So one thing we could do is, so we know 2 is a prime, and we know that the remaining multiples of 2 are not primes. So we should filter those out, right? So what do we get in no 2's? We basically get only the odd numbers, greater than 2, between 2 and 20, right? So no 2 will be 2 to 20, which is 2, 3, 4 up to 20, without anything that's divisible by 2. So meaning we'll let pass only what's not divisible by 2. That's what this little predicate or Boolean function tells us. Okay? So the filter passes only what's not divisible by 2. All right. So that is a good start, because now we have we have numbers up to 20 without multiples of 2. And then what's the first number in that list, or in that stream no 2? 3. So is that a prime? Yes, exactly. Okay, so that's good. So we found our next prime. So how do we eliminate the multiples of that next prime? Well, we could start with a no 2, and we could filter out the multiples of 3 as well. So now we are left with the numbers up to 20 without multiples of 2 or 3. So we'd have, is 4 in it? No, because we already got rid of that earlier, right, when we said no 2s. What's the next number?
5.
That's right. Is that a prime? Exactly. So that means, now we can say we're kind of discovering a pattern. Yeah, so always, when we take what we got so far, the first item in that is a prime. So we'll remember that, and then we'll filter out the multiples, and then we'll get the next item, the first item of that, and so on. So the pattern is kind of like this. We take our previous result, and we'll filter the multiples of the first item of the previous result. And that gives us the new list we're working with, and the first item of that is the next prime. And then we'll filter out the multiples again. So see here, an iteration pattern emerges. I tried to put a lot of comments in here so that this would make sense when you look at it later. So we always, in each step, we eliminate multiples of the first element of the current sequence. The successive first elements are the primes. So we can define this recursively. First of all, we can have the predicate for the filter. So we can, let's see, right, then we can have the actual filter, right? So a stream without multiples of n is just that stream filtered by that predicate, not divisible by n. Okay? So that's basically, we could describe this filter here as without multiples of 2, that's without multiples of 3, and that's without multiples of no 3 dot head. Okay. And to define the primes recursively, okay, we'll say, all right, if we have an empty stream, that doesn't have any primes. Right, if we have a non-empty stream, and here it's the caller's responsibility to start with 2, not to start with 1. It'll mess it up. So start with 2. And so if we start with 2, and we want only the primes in that finite substream, we'll assume that the first number is a prime. I mean, we got to start with 2 for the recursion to work. That's our base case. And that followed by the stream, which is again like a list, followed by the, let's say, if we have the original list, right? So let's say 2, 3, 4, and so on. So we start with x being 2, and then we have 3, 4, 5, and so on. So we take that, remove the multiples of 2. That's what we have here, and then we recursively do the remaining primes in that. Does that make sense? So it's basically taking that recursion pattern at the top. We're going one at a time, one prime at a time, starting from 2, until we've exhausted the list. Okay. So I got to wrap this up. All right. How do you prove that that's correct? Well, the usual thing is for recursive functions over structures, you do a structural induction proof using case distinction. The usual thing. Just like natural numbers, you do case distinction. Is it 0 or is it 1 more than a natural number for which you already know that it works, using the piano axioms. So it's very similar but generalized to structures. All right, so let's test these things. So let's give that a name. So to 20 is the range, 2 to 20 as a stream. And then our expected value would be the primes in that range. Okay, so I just wrote them down manually. And then our test, so we don't have to repeat a lot of stuff, so we're following the DRY principle. Don't repeat yourself. So we just define that testing once, and we can say test this function, test that function. So we're using higher order functions. The subject of the test itself is a function. So we're testing it using just this one example, but we could test it using multiple examples by having multiple assertions here. Okay. So that one, passes the test. But now the question is, can we do it without, because we're trying to go in the direction of not repeating the same kinds of recursion patterns all the time. So the question is, can we write it as a fold? And we'll wrap this up next time. But the answer is, well, yeah, we can write it as a fold. The question is it as good as the recursive answer or solution? And you'll see that no, not really. And then the question is there another recursion pattern that we can use to write it instead? And is that one as good as the original? And that one, yes. So take a look at this. Most of it is comments. There's very little code. So we'll take it over here, and then we will start doing that stuff. Again, these are intimidating. This is intimidating terminology, but I will make this more approachable. So it's a joint learning experience. But the examples that I finished recently, I think will help tremendously, because they certainly helped me a lot. So anyway, all right. So that's it. I think we're on time. So the idea is for everybody who's available to be able to go to the big data talk. All right. So everybody knows about this, right? It's today, right? Back in Lewis Towers, the 13th floor ballroom that they have. Right there, the big ballroom, and there might be, again, a few bags of chips left, so let's try to get some of those. All right, any questions, comments?